Water, water everywhere, not a drop to drink. That is the challenge facing the world today, a challenge to which science must find a solution. Water is the life of agriculture. It is also critical in industry to keep factories clean and functional. And of course, water is the mainstay of human life. The single most important source of water till now is rain. Falling directly on the land, it fills up countless rivers and tributaries. India receives a colossal 4,000 billion cubic meters of rainwater every year, the bounty of being a tropical country. Yet, it is also estimated that 3/4 of the total rainfall is lost as runoff to the sea. Not only is the water lost, it also robs the land of another precious resource, topsoil. Meanwhile, the global demand for fresh water is doubling every 20 years. Yet water resources available per person are just half of what they were in 1960. By the year 2025, these will plummet further. Of India's available water resources, only 1/4 is available for use as surface and groundwater. On the other hand, the quality of existing water resources is steadily deteriorating. Discharge of domestic and industrial effluents compounds the problem. A staggering 30 billion cubic meters of industrial water goes off with over 3/4 of it untreated. Worse still, it pollutes the source of potable water. Activities on land are the source of about 80% of all marine pollution, including sewage, industrial effluents, fertilizer runoff, heavy metals, and persistent organic pollutants. If water is not conserved, India may soon join the list of perpetually drought and famine-prone nations of sub-Saharan Africa. Yet, there is one unimaginably large source of water available, the sea. India has a coastline of over 5,000 kilometers, bordering the south, west, and east parts of the country. There is only one reason why all these millions of liters of water cannot be used for agriculture or for drinking. Seawater contains salt, 35 grams per liter. Even 1/10 of this proportion is harmful for a human being to drink. Can science and technology do anything to preserve this bounty, to save India? Yes, it can. Experiments at the Bhabha Atomic Research Centre, India's leading thermal and nuclear research establishment, demonstrate how. Over the past 15 years, scientists at BARC have developed both desalination and effluent treatment and water reuse strategies. They did so by closely observing nature's own method of providing fresh rainwater and reusing water. Nature has been using seawater for thousands of years. It creates rain by the process of evaporation caused by solar heat. At the same time, plants have a unique means to suck up water and nutrients from the soil. Thus, nature recycles billions of cubic meters of water every year. Growing human needs require a faster and controlled process to desalinate water, a process which will also clear the water of impurities. The Bhabha Atomic Research Centre was the pioneer in desalination research in India.
As far as coastal area is concerned, it is possible to convert abundant seawater into fresh potable water. This method is called desalination, that is removal of salt from the sea to make the water potable or usable. The desalination technologies are normally based on two processes. One is thermal, where the seawater is evaporated and the condensate is used as for industrial purposes and also for potable purposes. The second process is called membrane process, where the seawater is pressurized into the membranes, which have selective properties that they do not permeate salt and permeate only solvent or water. Hence, the water coming out through the membrane is potable quality water.
In membrane-based desalination processes, development of the appropriate polymer is important. The Desalination Division at BARC has a polymer development unit equipped with all the necessary infrastructure. The process begins with the production of polymer pellets. The polymer pellets are now dissolved and cast into a sheet form. The membrane is now ready for use in plate module. Long sheets of such membrane are rolled in spiral module configuration. It is rolled up and inserted in a metallic cylinder. These membrane modules are used as a building block for designing reverse osmosis desalination plants. Reverse osmosis is a pressure-driven membrane process whereby brackish water, seawater and effluent water is desalted to yield potable as well as process water. A total of 9 critical parameters have been identified to monitor and assess the plant performance. Pressure, feed flow, temperature, pH factor, turbidity, filter and module differential pressure, product quality, and chemical dosing tank levels. Seawater is brought to the plant through mild steel rubber-lined pipes. It now enters the clarifier unit. Coagulation is achieved by dispersing ferrous sulfate along with polyelectrolytes in the seawater before it is released in the flash mixer. The suspended impurities are removed in the inclined plate solid liquid separator, also called the lamella clarifier. The sludge generated is periodically drained. The clarified water successively passes through pressure sand filter, activated carbon filter, and micron cartridge filter. The pressure sand filter reduces the load from 40 parts per million to less than 1 part per million. The activated carbon filter removes the organics and the free chlorine present in the filtered seawater. Acid and antiscalant are injected into the pipeline to avoid scaling. Each dosing system consists of a preparation tank, a dosing tank, and an electromagnetic metering pump. The micron cartridge filter helps to restrict any particles larger than 5 microns. Sampling points are provided at each stage to test turbidity. A rotameter helps the operator to monitor the inflow of seawater. The reverse osmosis process begins with the pre-treated water being pumped with the help of a triplex plunger pump and passed through the reverse osmosis modules. The product and reject flow are monitored to assess the recovery. The post-treatment part revolves around making the water suitable for human consumption. This includes degasification to remove CO2 generated during the feed water acidification. Alkali dosing is then done for pH correction before final storage and distribution to users. In the years to come, this indigenously developed desalination technology will prove of great help in fighting the water crisis. Experiments are on elsewhere too. The Central Salt and Marine Chemicals Research Institute, Bhavnagar, the National Chemical Laboratory, Pune, and the Defence Laboratory, Jodhpur, are working on small-size membrane desalination plants. At its plant in Trombay, the BARC is also operating a 425 cubic meter per day thermal desalination plant. Based on this valuable experience, BARC is in the process of setting up a gigantic 6,300 cubic meter per day nuclear desalination demonstration plant at Kalpakam. Successful desalination plants have been in operation in the Middle East, the USA, and in South Europe. But this is the first time that an experiment of such large scale has been undertaken in India. As we enter the 21st century, India's population will have crossed the 1 billion mark. Water scarcity could prove a major crisis. Water, water everywhere, not a drop to drink, the poet lamented. But thanks to desalination technology, it is now possible to disprove the poet. Water, water everywhere, every drop to drink.